Oh, welcome to the third and final lecture on message passing paradigm. In our previous lecture, we discussed about point to point communication. We discussed that there are two broad class of communications. One is point to point, and the second is collective communication. So, in the first category, that is point to point communication, we focused on MPI send and MPI receive, the most basic message passing communications. Both MPI send and MPI receive are blocking operations. We have already looked into these different RT attributes which we pass through these two calls. The important points which we need to recall is that data to be sent by the sending process is copied from the user memory space of the sending process to the system buffer. So that's the first part. The data is sent from the system buffer over the network to the system buffer of receiving process. So in the first part, the data is sent by the sending process into the buffer, that is the system buffer, and then this goes through the network to the system buffer of the receiving process. So as we discussed earlier, that network is going to play an important role. So by network capability, I mean the bandwidth and the latency of the network. So this is going to determine the overall performance of the code. Now the receiving process copies the data from the system buffer to the local user memory space. Now these communication modes has both blocking and non-blocking primitives, which we have already discussed in our first lecture. So basically in blocking point to point communication, the send call blocks until the send block can be reclaimed. So what we mean is that the send call is blocked until we guarantee that this send operation has been done successfully. Similarly, the receive function blocks until the buffer has successfully obtained the contents of the message. In the non-blocking point-to-point communication, the send and receive calls allows basically the overlap of communication with computation. So communication is ideally done in two phases, the posting phase and the test for the completion phase. Uh, Two important overheads which we encounter during MPI communication is the synchronization overhead and the system overhead. So synchronization overhead is basically associated with the time spent in waiting for an event to occur or another task to occur. Whereas system overhead is the time spent when copying the message data from sender's message buffer to network and from network to the receiver's message buffer. So these are two important overhead which are associated with MPI programs, and we need to reduce these overheads as much possible. Um, so if you recall the MPI send and MPI receive function calls, there are couple of arguments which can be treated as a wildcard argument for both the source and tag. For example, we can set the source as MPI any source. Then any process of the communication domain can be the source of the message. Similarly, if we set the tag as MPI any tag, then messages with any tag are accepted. On the receive side, the message must be of length equal to or less than the length field specified. Otherwise, there can be errors. Last time we discussed about MPI status, one of the arguments in the receive operation, a receive call. So this status variable can be used to retrieve very important information. So this is basically a data structure which contains information regarding the source, the tag, error. Also, you can understand what kind of errors has happened. So we can use this contents of this source or the tag or the error in this MPI status argument. MPI get count function returns the precise count of data items received. So, what is the actual amount of data which we received? Because in both the send as well as the receive calls, we mention the amount of data which we are going to send. So, we have to make sure that whether the corresponding amount of data has been received by the receiving process or not. And MPI get count function helps us in verifying that. There are many situations where we can encounter deadlock, and we need to make sure that such situations does not occur. I'm just giving one example. So for example, let us assume this is the code. So here you can see there are two processes involved. This is basically, I mean, point to point communication. So from point 0 or process 0 to process 1. Now process 0 wish to send A and B to this process 1 and process 2. Now, if you look into this process 1, so process 1 is supposed to receive B, but it is supposed to first receive A, because here you can see that MPI, the process 0 is sending A first. So this is a integer variable, and then this is the um, um, uh, point where it is sending. Okay. Now process 1 is supposed to receive this A from 0. These two are basically tag 1 and 2. So you can see the tag associated with this first send call is 1. So process 0 wishes to send A with tag 1 to process 1, and process 1 is supposed to receive that A from process 0 with tag 1. Now the problem is, since MPI send is blocking in nature, so once this call has been initiated, it will get blocked unless it is properly received by the process 1. Now on the receiving side, process 1 is basically looking forward to um, the first receive, which is it wishes to receive, is basically B. But on the other hand, process 0 has actually sent A. So ideally it should have received A, but it is trying to receive B. So there is a kind of deadlock, because B will never reach, because MPI send A is waiting for the process 1 to send it a message that A has been received properly. But on the other hand, process 1 is actually looking for the item B to arrive. So the simple solution to overcome this error is basically reverse these two statements. So this MPI receive A should be the first one here, and then the second operation should be MPI receive B. So we have to be very careful while writing the code. Similarly, we have other important MPI calls such as MPI send receive, which basically helps in simultaneously sending as well as receiving messages. So our arguments are very similar. So it basically helps you in to accomplish both the things together, sending as well as receiving. Okay, now till now we have discussed about the blocking send and receive. So that is MPI underscore send and MPI underscore receive. But if we are interested in overlapping communication with computation, then we have to use a non-blocking send and receive operations. So the calls for non-blocking send and receive operations are basically MPI underscore I send. So the only difference is there is an I. So that's how it identifies that whether the send operation is blocking or not blocking. And these operations return. These operations means these non-blocking operations send and IPI I send and MPI I receive. These operations return before the operations have been completed. So we need to test whether these operations have been completed successfully or not. So function MPI tests whether or not the non-blocking send or receive operations identified by its request has finished successfully or not. But this is going to be much more efficient if done correctly, if implemented correctly, compared to the blocking send and receive. Okay, now let us go to the second kind of communication, that is collective communication and collective computation operations. So MPI provides an extensive set of functions for performing collective communication operations. Each of these operations is defined over a group corresponding to the communicator. So if you remember, a communicator is basically a group of processes, and we can define a communicator which consists of either all the processes. So by default, the MPI COM world is the default communicator, or we can create communicators with less number of processes. So all processes in a communicator must call these collective operations. So I'll look into some of the important collective communication calls. So this communication pattern that involves all processes within a given communicator is known as collective communication. So primarily, there are three kinds of communication calls. One is associated with synchronization. The second one is associated with communication or data movement, and third one is more about collective computation. So we can clearly see the difference between these three different kinds of collective communication or collective calls. So in the first one, that is synchronization, what we are trying to do is we want to reach to a synchronization point. So we want to create some kind of synchronization among all the processes. The second one is more about data movement. So, because in the previous case, we are just interested in data movement from one process to another. So that's why we call it point to point communication. But here we are talking about data movement from one to many or many to one, and these kind of movements are basically achieved through spatial collective calls. And we might be interested in doing some kind of collective computations. Computations which involve participation from many processes, so those can be achieved through spatial collective calls. So we'll take one example from each of these categories. However, we must remember that all collective communication is blocking in nature. So let's first look into a particular call from the first category. So the first category is basically synchronization category. So a very important function of the first category is MPI barrier. So how it helps in synchronizing several processes can be understood from this schematic. So suppose there are four processes, P0, P1, P2, P3. However, if you assume this horizontal direction as time axis, so you can see that they have arrived at this point at different times. So let's say that P0 finished first. So let's represent this time with an arrow. So uh, let's say that because P0 arrived first, so and we want to synchronize all these processes, so it has to wait for a longer duration compared to other processes. So after that P3 arrived, then P1, and finally P2. So once you put this MPI barrier, which is a synchronization call, it will just make sure that after this call, uh, all these processes resume at the same time as it goes forward. So it basically creates a synchronization in the communicator. So in this communicator you have four processes. Each process when reaching the this MPI barrier call gets blocked until all the processes in that particular group reach the same barrier call. So we can see how we can use MPI barrier to achieve synchronization. Now let's look into an example from the second category. So if you remember, the second category is basically the communication or data movement category. So one other interesting call is MPI broadcast. So the call is basically um, represented with this function called MPI underscore broadcast. So you have five arguments here. So what we are trying to do here is that suppose you have four processes, P0, P1, P2, P3, and you have a value which is present with P0. So let's call that is this root process, and you wish to send this a which might be, which can be simply an integer or an array, to all other processes in that communicator. So that is this communicator. So we can achieve that using this broadcast call. So instead of doing one-to-one communication with each of these processes, so otherwise this would have involved send receive between P0, P1, P0, P2, P0, P3. Here, simply with one call, we are sending this particular data to all the other processes involved in this communicator. So, a collective communication call where a single process sends the same data contained in the message, this is the message, to every process in the communicator. All the processes invoke the MPI broadcast call with the same arguments for root and this um, communicator name. So everybody basically gets to know that it is coming from the root, which is P0 in this case. We can look into another example from the third category. So the third category is this collective computation category. Let's take an example of reduction operation. We have already done reduction algorithm in one of the previous lectures, so we know how this algorithm works. So basically, what we want to do here can be understood with the help of this schematic. Suppose you have four values which are present at these four processes. So process 0 has A, process 1 has B, process 2 has C, and process 3 has D. And we want to find the sum of all these four quantities. So one way to do that is either all of these processes sends its value. For example, P1 sends the value of B to process 0. Similarly, P2 sends the C to process 0, and P3 sends the D to process 0. And finally, process 0 finds the sum of all this number, or we can simply achieve this using this reduction call, which can be called using this MPI underscore reduce function. So here we have to mention the root. So basically where this final sum will be available. So all the processes will send their individual values to this root, and we have to also mention the operation, what kind of reduction operation we are interested in this case it is sum. So this diagram basically we can understand it through this particular call. So you can see MP underscore reduce, and you can see the 0. So this is basically the root process, so that is where the A is present, P0, and we have to mention that we want to do a sum reduction, so therefore we are calling MP underscore sum. These are integer in nature, so we are just mentioning that these are float in nature, so we are mentioning the data type here. This is the count, and this is where the results will be stored. Okay. So we have looked into three different examples from three different categories. So in reduction operations, several options are available. We can achieve this kind of operations through these calls. We can find maximum from a group of numbers, minimum from a group of numbers, sum, product, uh, whichever operations fall under reduction category, which you have already discussed in one of the previous lectures. Now let's look into a summary of some other API operations. Let us consider that there are four processes. So process 0, process 1, process 2, and process 3. Now you can see an asterisk here. So this is because we have assumed that the process 1, that is process with rank 1, is designated as the data gatherer or the scatter process. And A, B, C, D, these variables, they can be scalars or they can be arrays of any data type. So here we are just looking what will be the output of these four operations. Let's say we do a MPI broadcast. So as we have discussed, here the root process is one, process with rank 1. So basically this process has this value b, so this will be broadcasted to all other processes. So after this operation is over, all the processes, that is process 0, process 2, process 3, will have this b. If you use MPI gather, then process 0 has A, process 1 has B, process 2 has C, and process 3 has D. If we use MPI gather operation, so we can gather all this value and put it at process 1, because process 1 has been designated as the gather process. Similarly, if we use all gather, then first these all these values will be gathered, and then it will be communicated to all the processes. So all the processes will have A, B, C, D. Similarly, we can have a scatter operation. So here, suppose we have A, B, C, D, and we wish to give it to other three processes. So A to process 0, C to process 2, and process 3 is supposed to get D. So you can use a MPI scatterer. MPI scatterer will help us in achieving that. There are many other collective functions which we can look into any of the available MPI manual. And as per the requirement of the applications, we can use these collective functions. There are other interesting collective operations which are available. For example, let's look into this diagram first. So suppose there are six processes, process 0, 1, 2, 3, 4, 5, and each of these processes has some value. Let's say 15, 17, 11, 12, 17, and 11. Now we want to find um, what is the maximum or the minimum of these six values. So as we can see, minimum is 11. However, that is present at two processes, process 2 and process 5. Similarly, the maximum is 17. So minimum is 11 and maximum is 17. So 17 is present at process 1 as well as process 4. So if we call MPI max lock, what it will do, it will return us what is the maximum value. So if you are using max lock, so we can see the maximum value is 17, so it will return that value, and it will also tell us which process has that maximum value. So basically, if two processes have that maximum values, so the smallest among those processes will be given as an output. Similarly, for the minimum lock, mean lock, we can see the minimum value is 11 and it is present with process 2. These are very useful in some particular applications. There are other operations such as MPI all reduce. If the result of the reduction operation is needed by all processes, because in the previous example we have just seen MPI reduce. So here the result is only available with P0, but if we want that the result has to be available with all the processes, then we can use MPI all reduce. We can also use MPI underscore scan to perform scan operations. We have already discussed the scan algorithm in one of our previous lectures. So let's look into the trapezoidal rule example. So integration using trapezoidal rule, which we discussed in our previous lecture, using point to point communication. So in that particular algorithm we used only MPI send and receive. So I'm not going into the details of all these declarations. What I'm going to highlight is that, if you remember, um, we need to pass this information, that is from we are doing an integration from a start point to the end point. Okay, so we want to pass that particular information to all the processes. So you can simply do a MPI broadcast, and you can see this is 0. So the process 0 is calculating this endpoint 0 and endpoint 1. So the left endpoint and the right endpoint, so the start and the end, and this information is basically sent to all the processes. So only process 0 uh, calculates that, and it broadcasts these two values to all other processes. Once these two values have been provided to all other processes, then the rest of the process can figure out, it has to do the integration on which sub interval, because it can always calculate its own local A and its local B. So each process is basically responsible for calculating the integral between these 2 points, and by using its rank, it can always figure out that information by using the endpoint, the left endpoint, and the rank information to figure out the local A and local B. And then it can use this function, trapezoidal trap function, which is basically the trapezoidal function, and it will get its integral. Once this uh, integral has been calculated for the sub interval, then we can use MPI reduce to pass that integral to one of the processes. In this case the root process is 0, so you can see 0 here. So all the processes basically sends their local integral to process 0, and process 0 finally gets the final sum, and we can print that final sum um, just through a print statement in process 0. Now, what are the important errors and debugging issues which we may encounter while doing empirical programming? Um, as we have understood, because it involves several processes, so debugging is definitely more challenging compared to serial code. Some of the important reasons for the program to hang, or we can get into some kind of deadlock, is that the send has no corresponding receive, or the receive has no corresponding send, because uh, this kind of parallelization is not automatic in nature, and a programmer is completely responsible to introduce the parallelism explicitly in the code. So the programmer has to make sure that if there is a send, there has to be a corresponding receive, and vice versa. Other problems which may occur is like send receive pair do not match, or the tags do not match. Then well, we have put some condition in terms of rank, or process ID, and it never occurs. So the way we expect it to occur, it never occurs. So that can also leads to some kind of deadlock, or the program can hang. It's very common to get this segmentation fault issue with MPI codes. When you try to access memory, which is not allowed to access for a particular process, then we can encounter this kind of segmentation fault. So basically, out of bound errors, we should always use a out of bound flag to figure out this kind of problems. Or suppose we are using a non pointer as a pointer, then also we can get a segmentation fault. Debugging parallel codes is difficult, and we might need special debugging tools. There are many good open source tools which are available, and we can take help of those tools. It is also important that what is actually happening on each node, because there are many nodes which are associated with a MPI program, and problems can occur in a particular node. So it's very important to figure out what's going on in each node. And while debugging, we can always take help of print statements in each node to figure out whether we are able to pass or send the receive data in the way we expect it to happen. Or we can use debuggers which are compatible with MPI. Now coming to the compilation and execution part. So in the cluster, all of you have access in the cluster. So this compiler is already installed there. So this is basically for C. So you can use MPI-CC. Then you can give the file name, which is basically with an extension of .c, and then you can get the executable. So basically, a dot out. So once you have created this, generated this executable on that a dot out, then you can execute it using MPI exec function, or we can also use MPI run. So suppose we want to run this executable on 24 cores, and we want to have 8 cores from 3 nodes. So what we can do, we can create a machines file. In this machine files, we can put the IP address of each of those compute nodes, and we can also mention how many cores we want from each of these compute nodes. So what I mean to say is, suppose you have 4 compute nodes, and each compute node has 16 cores or 16 processors. So total you have 4 into 16, 64 available cores available with you. Now you want to execute your code with on 24 cores. So you have choice. Either you can get 16 from node 1 and 8 from node 2. So then you can just include the first two statements. So you have to make slots equal to 16 and slots equal to 8 here, and you just give the IP address of the first node and the IP address of the second node. If you want to have 8 cores from all the 3 nodes, or 3 out of 4 nodes, then you have to put the IP address of the 3 nodes and how many slots you want from each of these nodes. So you can write a simple MPI program and execute it on the cluster. So this is the final lecture on MPI programming, message passes paradigm, and I think we have discussed most of the important topics in MPI programming, and the important calls which we have discussed, for example, MPI send, MPI receive, MPI broadcast, MPI scatter, gather, MPI barrier. So these are very important calls, and most of the times sufficient enough to write complicated programs. In our next lecture, we'll discuss another topic on parallel programming. See you in the next lecture.